Okay, so first of all, couple of just little points. Apparently, it is possible to do this problem. We have two, if you like, existence proof. Paul was able to do it all on his own without talking to me even once, basically indistinguishable from my solution. So, as you say, he doesn't work here, so it doesn't matter. But to demonstrate that even people employed at A9 could program, there is an example here of Hernan, who was able to do a rather beautiful job. I haven't seen his code. He never showed it to me. But we talked about it, and apparently he got it right. So, we have existence proof of one person at A9 who could finish things like that on his own. I still recommend that more of you try to do it in the future. Whenever we discuss it, it's just a challenge, guys, to try to see if you could program. I have to try to encourage you. All right. So let me start with what we had. Could we go to lecture 8? There are a couple of files there. Just a reminder of what we had. First of all, are you at lecture 8? There should be. Okay, so why don't we take a look at the binary counter, which we worked on last time around, and I made one tiny little change in it. Just let me introduce it. We'll simplify our code. What I did, I defaulted the second template argument. Okay? Basically, the idea is that if you have an operation is defined on some type, and if you could extract the type from the operation, I do. That's the default. If you do not want to do it, don't do it. But as we shall see, it will simplify our code a little bit. So I planned to do it last time, but with all the commotion, I forgot. So this is one thing. So remember, we have this binary counter, which again would allow us to do things. And in order to see how we use it, I don't need to use this. Let us go and look at the second file, which will show us how we find minimal element with the help of binary reduction. Of course, we could find minimal element without the help of binary reduction, without the help of binary counter. But it's very instructive now to see how we find it with its help. People could see it, yes, right here. So what we do, again, we go through, we add every iterator to our counter, and the counter, as its operation, uses this. It's a very simple operation. It compares the values and keeps the pointer of the smaller one. Let us carefully look here. This is the operation which the counter will use. What does it do? It compares two pointers, two iterators of any kind, actually, right? X and Y. And depending which one points to the smaller, keeps it. Make sense? It's very simple, guys. I really cannot say much more than it compares, and if the value of y is smaller, it retains y, it returns y, otherwise it returns x. Yes? So that's what it does. So we use this for our counter with our counter machine. So we're throwing one iterator after another. And then after we're done, we do reduce on the counter machine. And we get back the iterator pointing to the smallest value. All right? Again, Nick was asking, so why do we need this complicated thing? Well, we need this complicated thing because we will be able to solve a more complicated problem with it. Right? Of course, here we don't absolutely need it because we could just have a simple loop. But the problem which we're going to look at now, of course, is more complicated, which we cannot solve with a simple loop. And then we shall see that the same counter machine will appear in literally dozens of different algorithms and will help us to solve them. Okay? So our goal is now to somehow modify these two pieces of code. These two pieces of code are basically things which we need to modify to solve smallest and second smallest problem. But here we need to have another detour. You see there, do you remember the algorithm? The algorithm is, as we described it, as we're going to do binary reduction, but every time we play a game, the guy who wins is going to add the loser to his little list. I mean, having the little list following the prescription of the Mikado is very good. Right? So, but to have a little list, we do need to have little lists. Because vectors would be a little tricky. You see, the vectors are not optimal for this case because they are going to be occasionally reallocating, and too often in the beginning, these are going to be very small lists. Vector is optimized for relatively big things. All right? Moreover, what we need to do, we want to minimize the total storage which we use. Remember, there was this thing that we want to do minimal number of comparisons, but we also want to minimize storage. And we wanted to use what kind of storage? Anybody remembers? No, n would be too much. No. Polylogarithmic storage. Again, remember, somebody said? Well, you did say log. I misheard. I apologize. So yes, that's what we want to use. Log square. Well, we rather use log. We rather use constant one. But here I have to tell you, the best solution I know uses log square. Could we improve on it? I do not know, at least. This is for those of you who aspire to greatness, want to show what's the minimal bound. We already know what's the minimal bound on the number of comparisons. So if somebody wants to show the minimal bound on the extra storage, I think it would be a remarkable result. As far as I know, nobody knows what it is. But I think log square is pretty good. By the way, anybody could tell me what's the idea? How large is log square? Roughly, what is it? We discussed the log is 3264. Yeah, we discussed that, right? So what is log square in real life? No. Way too much. 512, guys. 512. Just once and for all. Remember, practically speaking, it's always enough. Well, how do I know that? 32 is pretty good log, yes? And it's going to be n times n over 2. All right? So what is n over 2 is 16. 32 times 16, that's about 512, I think. Right? So 512, practically speaking, is a plentiful storage, even if we're going to do billion of guys. Right? So our goal is to assure if we keep generating this little list, everybody is going to have a little list. And if they are vectors, there are going to be lots of vectors. But lots of them. No. Because while the counter is small, lots of guys go through the counter. And just about, okay, think about it very simply. Just about every other guy will have a list of length 1. Do you agree with that?
But only the winners.
Yes, and absolutely, but there will be at least n over 2 winners. Right? There are lots of winners. Potentially, they all disappear, but there will be n over 2 winners. You agree with that? We have n over 2 winners. That gives us clearly not logarithmic amount of storage.
The counter only holds log.
I know, but many people go through the counter. And then they drop out again.
We don't need to store their winners.
We don't. No. We absolutely could. I mean, yes, we shall see. We will be able to get by with logarithmic amount of storage. But
maybe we could reuse a small number of vectors.
maybe we can. But what I'm trying to show you is how to use classical, beautiful data structure, which you don't have right now, which will be useful in million of other contexts. Again, sort of, look, it's all cheating. You know, I pick an algorithm not because this algorithm is of paramount importance for your future work. I pick this algorithm because it allows me to do certain decomposition. First of all, teach you to do the decomposition. Second of all, show these components. It's like the counter, right? And now what I'm saying, there is a very, very useful thing which is which would allow us to use lists the way they're used in Lisp. Remember, once upon a time, long ago, there was a programming language called Lisp. And it had a very, very simple lists, which were based on 3 fundamental operations. Okay? For older people like Hernan, they remember what they were. They were cons, car, and CUDA. Get, a node is called cons. Car meant get first component. CUDA meant get second component. Of course, we're not going to use these terms, and we're going to somewhat extend our vocabulary from 3 to 4, because Lisp told us that there's this wonderful thing without which you cannot live called garbage collection. And we say, well, we don't really want to build garbage collection. For all the algorithms we want to use, we could do manual return. So we're going to have car, cons, car, CUDA, and free. Right? But we're going to build it so that it's going to be blindingly fast. What's the problem with building it blindingly fast? We want to avoid malloc. Malloc is evil. Malloc used to be sort of all right when I started working on STL, which was in 1993, 20 years ago. Right? But even then, I realized that it was way too slow to be used with node-based data structures. So what did I do? For any data structure such as list, I would keep a pool of nodes myself and sort of manage things. And it was relatively fast. But then people said, the first person was Bill Plauga at Microsoft, but then other people in GNU followed the example. They said, well, but if lists are like that, if they have a common pool and they just do pointer movements, then if you have multiple threads, you could have problems. So instead of solving the problem for multi-threaded case, they decided to solve it in general. They said, First, we're going to make our malloc to have locks. And then we're going to throw this entire Alex's pool management at all just away. And we're going to do full malloc. Now, lock, it's a function call, it's a lock, it's a very heavy iteration. And now all of our lists are going to be thread safe. And now people like you who do not use threads, you know that you don't use threads, but you pay. So they violated a fundamental principle which Bjarne Strustrup always insists, that people should not pay for things they do not use. You should never build things in the language and the standard library which people who do not use them will pay. Right now, everybody pays for the ability of multiple threads to sort of do list allocations out of the same pool, which actually nobody does, but everybody pays. So we want to avoid this problem. We want to build ability to use lists which are blindingly fast. What is the second problem of lists? So it's malloc. Traversal is, unavoidable. Obviously, if it's a list, you have to go through a link. But you don't want to go too far. You want to avoid memory fragmentation, right? Because if you have lists with nodes spread all over the memory every time you do, you have, modern computers, caches do not really help if you do long jumps. So we want to assure that our we have lots of nodes. Remember, we're going to have n over 2 nodes at least. Not at the same time. We will generate them. But at most, we're going to use log square. Right? So we want them to live in log square space. We want to have a little buffer where all the nodes, even if we keep generating them back and forth, reside in a small space, so we never, ever get a cache miss. Right? If you live in a small space, 512 of something, you will never get a cache miss, trust me. So what is the way we're going to go about it? How could we accomplish all of these wonderful things and write very little code? Bert actually told us the solution. Yes, he did, except in the wrong context. He said, let's use vectors. He made one mistake. He said vectors, plural. Right? So let us use one vector to implement many, many, many lists. That is the idea. We're going to have lists residing in a vector, which would allow us to do many things very, very fast. Okay. Are we ready to implement it? Okay. I'm going to cheat this time. I'm going to pick somebody I'm going to give this spoon. And it's going to be Hernan. Why? Because I want to be done with lists with fairly painless way. Yes? You want to talk or you want to type? Okay, he wants to type. Give him Emacs. He wants to type with Emacs. But he still will not just type, he will type under my guidance. Yes, I apologize, that's how it works. So let us see. So first of all, let us start building this thing inside out. What I mean by that is that somehow open Control-X, Control-F, list pool.h.
Documents, unshared.
No components shared. The course shared, code, lecture 8. Yes. list pool dot h. Yes, this is good. This is why it will be there. Okay, so let us try designing it from do not, yeah, you probably need to include vector. That's a safe assumption. But let us figure out what are the basic operations. So we'll have some kind of a class. So we could start, and probably will be template with some arguments. So we could say template, angle bracket, dot, 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 angle bracket. We'll figure out. And then it has a name. We already picked a name, yes? Class list pool. And then inside this, we'll have basic operations. What is it on? Yes. So even before we implement them, let us think about how it is going to work. So this pool is an object. And there are many lists outstanding, yes, against that. So what we're going to do, we need an operation. He says const CUDA free, but we want to name them appropriately for younger generation, for people who do not know about const CUDA. And so modern names, yes. Let us think about what is a good modern name for car.
Value.
Yes, because it's a value at the top of the list. So, okay, so let's try to write it.
What are we going to call it?
Value? Yeah. Yes. We don't know what we should define. I don't like it. I don't like it. What don't I like? Okay, no. Okay, here's the spoon. What don't I like?
What don't you like about what?
What you just wrote. No. You shouldn't have deleted it.
This?
Yes. I said I didn't like it.
I need to.
Well, there are a whole bunch of things I didn't like. But I would claim I don't like what you return.
Oh.
Not at all.
Okay, it's a reference.
Or I actually claim there are two versions of value. Okay? There's one version which will return a reference. Why it's a good version? Because sometimes we might want to change a value. Right? And what will it take?
It needs to know
Which list?
which cell, yeah.
Which list? Let's call them list. And let me suggest a very simple solution here. We will call it list type. We don't know what it is, but we'll just say list type. And we'll call it X. And this is good. This is very good implementation for the time being. Right? But I claim we need the second version. Why do we need a second version? Well, guys, we're not just trying to solve our problem. We're trying to build a component which people will use for ages to come.
You want a version that doesn't allow the color to modify it?
Yes, constant version. And it's called value, list. No. No. Go further. How do you say that something is a const? A member is a const. This is C++ things, but the way you do it is by saying const right here. This is known as overloading on const. It's the same method. It's the same member function with the same name. but depending on if your pool is constant or not constant, this, no, what did you do with this constant? You need both.
Okay, so we're saying that the list is const,
The pool is constant.
and the reference we're returning is also constant.
That's the meaning. Otherwise, saying that it's constant, it wouldn't make any sense because people will be able to go and modify things.
We have two versions, ship it.
That's how we usually do, yes. But you see, sort of, this allows us, okay, by the way, to deal with two things. It's not just car. Inside this, there's hidden another Lisp function. Which Lisp function? Or which scheme function for younger generation? We do not remember. There is car, and there is a mutative function called, come on, you should know this. What is it? What is the mutative function which allows you to modify car? It's called set car bang. Yes? Or for old Lisp people, it's called,
Set of car.
well, or for old Lisp people,
I'm not that old.
not that old. For old Lisp people. He is blacking out. Everybody is blacking out. Replaca. Replaca. I mean, this serves as our replaca. Because now we could say value of list assign, and it will go there. Do you see? So we have replaca and car together. I'm talking to non-existent, apparently, Lisp community. I assumed you knew that. What did you program in? I know, for like 8 years, right?
No, after I was an undergrad, I didn't touch it.
What did you program after you were an undergraduate? Java and Python. Wow. It shows, yes. As if it was Scheme, that was at least. They switched. MIT now is just this Python school, Pythonic school. Scheme might have been wrong, but it was great. So, okay. Let us ignore for a minute or two how we implement it. Okay, so we have value, and then we need something else. What do we need something else? Next, somebody suggested. Yeah, I think next. Yeah. Next. Yeah. And of course, he makes a mistake. Why does he make a mistake? Because remember, here I was able to get car and replaca. So here I want to be able in the same thing to get what?
We're doing CUDA.
CUDA and
We wanted to set CUDA too.
set CUDA in Scheme or replug-D in Lisp. You should have, I mean, come on, you programmed in real Lisp.
I'm using setf.
Setf does everything. It's a macro. But replug and replug, they are the primitives which allow you to manipulate the consoles. And here we will solve this problem how? The same way as we solved it here. Return ref and have two versions. I mean, you couldn't modify the tail of a constant list, right? In a constant pool. Okay. Now let me show you how you should program. I mean, we don't know anything about implementation, right? So, but let's try to write code here. which would allow us to delay the problem with implementation for a while. Right? So what we're going to say is there are some very secret hidden function, not visible to simple people outside. So these are public functions, yes? So you could stick a word public someplace on line 8, say, or no, 5. Because basic operations are obviously public. Some up there you will have some private stuff. And this private stuff would have a function, magic function now called node, which we don't know what it returns quite, but it will probably return a pair. Somewhere we're going to have these things containing nodes. So the function of node is going to take an argument of a list for a list. So it's the same time, list type X, right? And it's going to return something, a node. Why don't we say it returns node T? Reference and node T, const node T reference, overloaded, the same thing.
Is there a const here too?
Yeah.
Okay.
You see, it's all of this is mechanical stuff. It does not require thinking. We could produce lots of code without thinking, and we do. But let us see how we now could implement this stuff. So here, let's implement value. Probably need to say return. And then you probably need to say node of list type.
No?
Yeah. And what about this one? Yes. And what's about, I mean, you see, this is getting to be really simple. Yes? So we're done with cars and cooters, repluggers and repluggers. Of course, we have to implement this node function. Now we have to deal with two functions. Probably one is going to be called allocate, another is going to be called free. I'm not, it sort of makes sense, yes? And let's start with free. And the question is, does it return void? Could we make it somewhat more useful?
It could return.
Yes. You're returning the node somehow, but you could return to the user its CUDA, its next. Otherwise, the poor user, as we shall see, will have to save the CUDA and then to do free. So it's a convenient interface. No. These nodes are totally invisible to the user. No, and this is not a reference. Yes, it's a list type, but not a reference to, I mean, right? You're destroying the, I mean, you're actually destroying the reference to the list type. Okay, anybody suggests a clever implementation? So you have a node. Somehow he gives you a node X. What is the first thing you need to do? Yes, you need to save the CUDA. Otherwise, you couldn't return it. Okay.
I want to call it cooter, but
No, why reference? What? No, you never say x dot next. You haven't got it. Use public interface whenever possible.
I was calling the function I defined right above it.
Yes, so call a function you defined right above it. You are not calling a function.
Oh, yeah.
Yeah. Yes, like that. That's calling a function. Yes, you should always call a function you defined right above it. So now we come to a really tricky part. I mean, the function is going to have 3 lines, I suspect, and this is the only tricky line, because which will introduce something which we haven't heard about before. So what do we need to do with this node? Lord, could you say it in English? Okay.
We have a free list. We don't know what it is.
No, there's no pushback. What do we first need to do? Now, okay, think about it. You're a list programmer. You saved the CUDA. What now do you need to do? Thank you. Mutate the CUDA. No, not the free list. Not the free list. Free list will come in a second. But first thing you need to do, you have this node with 2 guys. Value, which you ignore. Never mind that you have a value. And its tail. So what do you need? You need to port the tail to point to the free list, yes? How would you do it? No, there's no CUDA. I mean, you have it all in front of you. This is this wonderful thing. Remember, how do you do replug-d? You need to do replug-d x free list, right?
Okay, so I have a list that I'm going to free altogether.
No, just one node.
Okay, so I'm freeing the.
One node.
Okay. So if I have a free list already.
You have a free list. Let's agree. What we are going to call it, guys? I think it's a great suggestion. No, you cannot do it. Yes. Yes. This is equivalent. Guys, this is once and for all, I'm showing. This is how you manipulate lists. You just go and put it still there. This is replug-d. Set f CUDA in your language. This is intermediate. Old timers replug-d, middle timers set f CUDA, young generation set CUDA, bang. Well, and you people don't know. They no longer probably remember that, right? No, but now you need to do one more thing. What else do you need to do? Of course, now this guy points to the free list. I'd listen to him. Why not? He's occasionally right. Right. This is the standard, guys. This is the standard. That has to be like that. In whatever context and whatever language. When you do things like this, what you do, you first attach You saved the CUDA, so it's not going to disappear. Now you could modify it. Now you're setting your global to this, and then you return CUDA. Yes? Make sense?
Yes, we've returned the first cell in the list to the free list.
Yes. If you want to return more, you could write a function outside of this class, and we shall, obviously. I mean, because it will exercise our class.
I mean, we could have said return this full list.
We could, why don't we do it?
You need to tell me because that's how I did it.
Okay, so let us try. Anybody thinks why this is the necessary thing? What should be the necessary thing for member functions? You do as little as possible to maintain invariance, and everything else should be done outside. If I give you this function, could you implement your function? Outside. Now, if you give me your function, could I implement this function?
Yes, I could break my chain outside and then free just one cell.
Yeah, but it's hard. It's much less natural. Right? So you basically want to have a pair function, one which makes one node, another one which eliminates one node. And then the rest, sort of, this is the minimal interface. Yes, but of course your solution does work for our problem, but not for the general purpose thing, which this is. Okay, so we're almost done with simple things. There are a bunch of things. So one more thing left. What is?
Now, when we return the cell to the pool, should we do something about the value that we have stuck in there?
That is an interesting question. The problem is that in our context, we don't. And I could answer the question now, or we could wait a little while. Okay, let me answer now, since you're a little bit ahead of time. There are two functions. There's, of course, function free, which we just did. But there is an equivalent function, potentially, which might be used, is free and clear. But let us not implement free and clear right now. What will be changed in free and clear between free and clear? How? That is harder than you think.
If we're storing a reference, we have a problem.
Well, if we're storing a reference, we're having so many problems you wouldn't believe. Never store references. Avoid references like a plague as a store. There is a wonderful thing to store, by the way. It's called a pointer. But if you store a pointer, that's what we will be doing.
We need to have a notion of what an empty value means.
Yes. And what is this? The closest we have to the empty value. No, 0 is not an empty value. I mean, it's not an empty value for a vector. What is an empty value? How do you construct an empty value? The closest approximation to an empty value we have in C++. No, we don't want your opinion. Very good. And how would you do it? This is correct, but how? What's the syntax? How would you write it? Yes. So what you would do, you would stick here, let us write it, but we will not do it here. What you will do here, before you, at any place, you would say value, of x. Remember how we do replacer? Something like that. So, but that, in our case, let us not do it.
I mean, before we were passing in a 0. We could do something like that too. For comparison, we construct.
It's not, I mean, typically, again, let me argue why this, while might be an additional method, is actually not a normal thing. Here we're actually changing the semantics. We're not any longer build containers. These lists are not containers. They do not quite guarantee the same thing as a container. Container guarantees that one container is gone, the values are gone. These are lists. There is no guarantee like that because, for example, you could split this list into 2 by doing replace. I mean, they could, there is no ownership. And this is why I recommend not viewing them at all as STL containers. People say, but isn't this terrible? No. STL containers are wonderful things when you want them. But that's not the case where you want them. You want this pool of we're trying to get as close to Lisp as we can without building garbage collection. By the way, if you want to build garbage collection, you could extend this thing and build garbage collection too. But it's not what I want to do at present. Yes? This is not, garbage collection is overrated. So I will eliminate this for the time being. And let us try, before we proceed to this delicious food, which is awaiting us now. The food is beyond your wildest dreams. Beyond. It's just, and it's on time, and they brought tablecloths. That good. So, do we go eat food or do we try to write? Maybe we go eat food. We do this? We finish? Okay. So, let us do one more guy. Which guy are we going to do? Allocate. Okay, so what should allocate take? What should it return, by the way? Well, let's start. I mean, that's the cookie which points to, we don't actually know what it is, but some kind of a cookie which points to the list.
So do we want to take the value that we're going to stuff in the cell?
And this is our model equivalence of what? This is model equivalent of what Lisp function?
Cons.
How many arguments does cons have?
It takes the value.
No. Cons takes 2 arguments. That's what Nick, how many arguments does cons take? 2. He says 2. Okay, so we should take 2 arguments. C, yes, very good. Somehow for the first, this T is popping out. Well, we'll have to define it someplace. For sure not that. You have 2 choices. You could either assume that this goes by value or by const reference, but not by reference. I would settle by value. There are probably little tiny things we will discover. So might as well do that. Call it next, call it next. Young generation doesn't know kudos. But I never heard of kudos.
Okay.
Yes, you can. But call it val. And call it drop E. Just or call it tail. Call it tail. No. Call it tail.
All right.
Okay. Now here comes the trouble. How do we go about it?
We're going to need a new node.
Where do we get new node?
Very beginning, the free list is completely empty.
And not just in the very beginning, it could be any time it could be empty.
So if the free list is empty, we need to do one thing. If it's not empty, we do another thing.
Okay, but I sort of think that there are two things which we'll have to do. And let's write this function from the end. What we'll have to do at the very end?
We're going to return the new head of the list.
We will have someplace you will have this new list. And you will get it somehow. And after you get it, what you will have to do?
I'm going to set its value.
And
I'm going to set its cutter to the tail that we got.
so let's do the end. I mean, always do what you need to do first. No, you forget. Never mind how you get it. Just don't forget, you have to set a value after you get it. At the very end, just put a new line. No. I would, of course, you have to set value before you set the tail. Why? Because it's aesthetically pleasing.
We could have whatever happens.
Interchange 37 and 38. Right? So now the question is, how do you get new list? And let me suggest something pretty amazing. Let us assume that you just write here free list. Let's just assume that you could just do it. Of course, you cannot do it. So this is almost done. We're almost done. It's a free list. Okay. Except we are not. So what we need to do? No. Here there is this thing called conditional. You might have heard. You see, next might be, no, we cannot do it. That would be terrible if you do it. The computer is going to melt right here.
Well, depending on some condition.
So before you do the condition, so what's the condition you need to check?
The free list is empty.
Yes. I would actually write it the way you said it, is empty, free list. And if it's empty, you do something very complicated we don't want to know. Else, let us see what if it's else, it's not empty. Then inside this else clause, what you could do?
Well, I set the free list to the second item in the free list.
Yes, do. Works, yes? So now we need to, now we know that free list is empty. Let me suggest something. When in doubt, invent a new function. So what you do here, you say new list equal for example, like that. We'll have to define it, but that we will do after we eat lunch. Right? But observe, we're actually done. We will have to define new node, which somehow gets it from wherever it gets it. But other than that, yeah, and it's empty, yes. But this is, we're sort of deferring things. Right? We'll have to discuss, just one more second before we eat lunch. Just could we look at them? Which one of them is public and which one of them is private? Are they? Okay, so I'm the customer of your wonderful list class. How do I find that list ends? What's your equivalent of null? What's your equivalent of null? So you want to keep your null private? You do?
No, I need a way for you to tell that you're at the end of the list.
Yes, that's the way. So this is a public guy. Do we agree with that? And this guy, nobody needs to know about, what is here? New node. This is a secret one. But this is, so I just wanted to sort of, all right?